Welcome back to Codex. Our speaker today is Stephen Gortler, who is the Robert I. Goldman Professor of Computer Science at Harvard. Professor Gortler is an expert in rigidity theory and computer vision, and today he'll tell us about invariant embeddings. Take it away, Stephen.
Thank you so much. If people have questions, just jump in as I go. This is called Invariant Embeddings. It's joint work with d.Then. You may have seen him speak about this work, in which case you might be a little bored, but I'll probably take a different point of view. I also spoke about this at Northeastern, and again, this will be somewhat similar to that talk. Nadav works in machine learning. I work in rigidity theory, but this is an interesting set of questions that really overlapped both nicely. So I'm going to start off from the world of rigidity and describe a notion called global rigidity. So let X be a d by n matrix. I'm going to think of it as n points in, let's say, R to the d. And okay, so here is R to the d. I'll draw that as 2 dimensions, and here is a bunch of points. And then there are going to be some pairs that I call edges. I don't know what, here's another point here, here's an edge, here's an edge. And what I'm going to do is measure the squared Euclidean length along these edges, and there will be m of them. Okay, so we've got essentially a graph G with vertices and edges, n of these, m of these. We have a configuration, I'll call the matrix X, describes that configuration. Here are the points, I measure them. So I'm going to say that the pair GX is globally rigid. So I'm going to define this. If I have another matrix Y, which describes a different placement of the points, okay, or some placement of the points, but it produces the same measurements. So all of the associated edge lengths matched between X and Y. Now, of course, one way to do that is simply to have the configuration Y to be some translation, rotation, and reflection of this one. That's called a congruence, so that's not interesting, okay? But globally rigid means that the only configurations Y that do this, that have the same m Euclidean length measurements on the edges, are related by a congruence, okay?
So question, do we receive the distances as a set, or do we see them as being attached to edges?
We're given a graph and they're attached to the edges. Good question. Okay, so here's in 2D some very simple examples. Here is a drawing in 2D, and this particular this is a graph and there's a configuration, and this is globally rigid in 2D. There is no other thing you can do to get these, whatever these lengths are, you know, some number here, some number here, some number here, and here, and here, other than translation, rotation, and reflection. You'll have to just trust me on that. Here's an example which is not globally rigid. I've drawn it so that these 3 points are exactly on a line, which meant that I could have taken this point and sort of in 3D flipped it over to here, like that, like a book. And that's not a translation, rotation, or reflection, but it certainly has all the same edge lengths. And so this is an example of something, a GX, that is not globally rigid. Okay, so before we go forward, are we all good with the definition of a GX being globally rigid? Okay, now note, if something's globally rigid, that means that given the graph and given the lengths, there's essentially only one way to draw the picture in d dimensions. Doesn't mean that it's easy to do that. And I'm not going to talk about computation and efficiency and those kinds of questions. This is more of an information theoretic situation where the measurements are sufficient in an information sense to give you X. And again, I'm also not going to talk about noise or those kinds of things. Now, as we move forward, translations are really going to sort of be beside the point. We're going to really be more interested in orthogonal transformations. And so in this setting, we'll just take the first vertex and just arbitrarily move it to the origin. And so now translations are no longer in the picture. And the congruences now are just going to be rotations and a reflection. And I'm drawing my pictures for d = 2, but I could do this in any dimension. 3 is certainly interesting in practice. 4 and higher is certainly interesting in theory. Okay. Now, global rigidity, looking and analyzing these drawings, that's actually a pretty tricky situation, pretty tricky to analyze. And so sometimes we try to look at an easier question, which we're going to talk about generic global rigidity. And it turns out the following is a theorem, that once we fix the graph and fix the dimension, then almost all configurations, that's X tells me where to put the points, almost all of them will be globally rigid, or almost all of them will not be globally rigid. Okay, it will not be the situation in converse that, like, half of them are half the time when I place the points, it's globally rigid, and half the time it's not globally rigid. Given the graph and the dimension, there's basically one expected kind of behavior, and then there may be some exceptions that are hard to find. Okay. Now, in the former case, when almost all the frameworks are globally rigid, then we're going to say that G, the graph, is generically globally rigid. I'll say GGR in D dimensions. And conversely, if X has the opposite property, we'll say that G is not generically globally rigid. So let's go back to this example. Notice here, I drew that point on a line. That's actually quite special. Let me draw it sort of generically. That's kind of a generic picture of that graph. And this one here, you could see I could flip it over and put it wherever it lands and keep these lengths the same. So in 2 dimensions, this graph is not generically globally rigid. Even though this specific example was, most drawings of this graph in 2 dimensions will be not globally rigid. And over here, let me draw this graph sort of generically. This graph, as long as I don't have these 3 points on a line, now this thing will be generically globally rigid. There'll be no other way to meet these length constraints other than, let's say if we set this to the origin, rotating or reflecting. Okay, so that's generic global rigidity. And so we can think of this, GGR in D dimensions as a kind of density of a graph. More edges means it's, in some sense more likely to be generically globally rigid, but it's really a notion of a graph itself. You don't need to, right? Because almost all of them are going to behave a certain way. So it's really a graph density type notion. It needs about n times d edges is roughly the minimal you would need just to have enough constraints to knock off the degrees of freedom. So nd minus roughly d squared is just ballpark what you're looking for. But it doesn't just depend on the number of edges. It depends on the details of where the edges are and where they aren't. Okay. Another thing I will mention is that this property whether given a graph, is it GGR in d dimensions or not, can be tested efficiently. There's an algorithm that can take the graph and give you a yes or no answer. Although it's not obvious what that algorithm would be. For example, you might look at 2D and think, oh, I see a lot of triangles, that must be relevant. But I will let you know that K33, I'm going to draw it generically, sorry, K33. So boom, 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 boom. That's not generically globally rigid, but K43 is generically globally rigid. So this is not going to have a necessarily very intuitive description, but there is an efficiently testable description, assuming you have randomness. Any questions? Okay, good. So GGR means almost all configurations will be determined from their lengths in d dimensions. But it does allow for exceptions. We've already seen that. That's how we started. This graph here was GGR, but it had this exception. So the question is, well, can we add a couple more edges maybe and find graphs that are going to be globally rigid, not just for most or almost all, but for all? Okay, that's kind of a reasonable question to ask. Now, it turns out the answer is no. We know that the complete graph complete graph. That graph is globally rigid for all configurations. But in fact, that's pretty much the only kind of graph that will have this unconditional global rigidity. So the main answer is no. For any non-complete graph, there's going to be some configurations that are not globally rigid. So here's an example. Let's just make d equals 1. Let's go to the line. Here's the line. Let's take 100 vertices. So let's take K100, and we're going to remove one particular edge, 1, 2. And I'm going to put 98 vertices here at the origin. And then I'm going to put vertex 1 over here and vertex 2 over here. And this is connected to all these guys, and this is connected to all these guys. But there's notably no edge between 1 and 2. So it's almost a complete graph. It's just missing one measurement to be from the complete set. But for this particular configuration, I can't distinguish this configuration from the configuration where this thing has flipped over to here on the line. Okay. So in the graphical setting, we can get generic global rigidity, but if we want to get unconditional global rigidity, we're pretty much out of luck. Really, genericity is, pretty much the best, close to the best that we could talk about doing. Again, any questions? Okay. So now I'm going to talk about another problem that comes from, I will just say, generally speaking, signal processing. It sounds like there's some harmonic analysis type people here, so they may know about this or a lot about this. And this is not exact. This is sort of a generalization of what people often call phase retrieval, but I'll just call it phase retrieval. And I'm going to think of this as a generalization of what I just talked about. So again, I'm going to have a matrix X, which is d by n. Let's make them all real numbers. And here's how I'm going to take a measurement. I'm going to hit it on the right with an n vector w. And then that's going to give me a d vector in R to the d. And then I'm going to take the squared norm in d dimensions. And that's going to give me a real number measuring the underlying signal x. Now, all right, that's a process. Now, no, why is that a generalization of a graph? Well, it's a generalization of an edge. If you want to measure the edge length, you could just take a vector w that's all zeros, a +1 at slot I, a -1 at slot j. And then this literally takes the vector difference in d dimensions between xi and xj and takes its norm. So you could have, in this setting, with the appropriate choice for w vector, modeled a single edge. Okay, so that generalizes, but we don't have to have zeros and ones. We could just put whatever numbers we want in here and call that a w. The next thing I want to say is that this is clearly a measurement that's going to be invariant to orthogonal transforms acting on d dimensions. So in particular, if I had a d by d orthogonal matrix O, and I threw it in here to the left of x, then that won't change the squared norm of what I measure. So we'll call this a w measurement. A w measurement off of x is OD invariant. Uh-oh, I seem to have I lost my zoom? I have. I don't know why. What's going on here? Got booted. All right, sorry about this. Let's see if I can get back in. Join meeting. No audio. Got it. Start video. Flip. Tilt. Place. And can you spotlight? I can't seem to spotlight it anymore.
I think that does it.
Did you? I don't know. Is it big on everybody's screen? My hand.
That's it.
Yes.
I heard of. That's a yes.
Yes.
Good. Okay. I think yeah. I think I can't. I wasn't. Okay. So where was I? Yes. This is an orthogonal measurement. Good. Okay. So in a graph, we have more than one edge typically, and in phase retrieval, we have more than one W. We have a bunch of W's. In fact, we have some number of them. We'll call that number M. Okay, so I do it again, and I pick another W. I get another number, another W, another number, another W, another number. Okay. So in the end, we've given X, which is in R to the D times N, it's a matrix, we get something in R to the M. And this map is invariant to OD. So this literally gives us a map from this object, RDN mod OD, to RM. And I will call this the phase retrieval map. Okay. Good. So now we have a question. Can we choose an M that's smallish, not like N choose 2 or something, smallish, so roughly N times D, somewhere in that kind of, or KND. And can we choose M, once we pick that M, can we pick some W's, 1 to M, so that this map is injective? There are no two different objects here that map to the same vector of measurements. In other words, every, not just most, x is determined, of course, up to orthogonality on the left from its measurements, not just almost every. Okay, and that's the question people in phase retrieval would like to talk about. And if we do that, again, there's another, you can think of this as a signal inversion problem, but it's also a map. There's this funny quotient space. And here we've mapped it continuously and injectively into Rm. Rm is going to be, bigger than this object, but we found enough room and a specific construction to map it injectively into this space. Okay, so this is the question. Again, when we restricted our W's to be graphical, the answer was no. There can always be at least some small set of exceptional guys, places where the map was not injective. But now we're allowing ourselves more general W's. And so, maybe the answer is yes. So that's the question. And
are you saying more general W's because we can take W to be +1 in one coordinate, -1 in another coordinate?
It could have 7 and pi and 22. It can have any real numbers in any coordinate.
But you're saying this is a generalization of the rigidity question, I think, because you can embed rigidity into phase retrieval.
Yes, you can embed it by restricting your W's to be edge indicator vectors.
Perfect. Thank you.
Okay, so that's an example. So it's an example of phase retrieval, but it's a very, very disabled example. It's very restricted in how you can probe X. Very combinatorial as also. In general, there's this moral that it's in all these rigidity problems, it's the fact that this is a combinatorial restriction that makes the behavior so subtle to analyze. If you sort of smear everything out and everything becomes just real numbers of various kinds, the questions become a lot more classical and sort of fall away much easier. And that's something that sort of has come up in things that we look at in the last, over and over again in the last couple of years. This is going to be an example of that phenomenon. So that was the question. Can we choose a smallish m and some w so that it's injective? And the phase retrieval people have an answer. So here is the answer. Let m be this big. So how big is it? Well, it's 2nd. That's the leading term, because I think of n as big and d as small. And then there's a little bit of this tail term. So I make it a little bit smaller, basically. I pull off d squared, add back in a d. So I call that, this is the tail term. And again, we have n vectors in d space. So there's only there's nd degrees of freedom. So if everything was just a linear system, you would just need nd measurements. And this is saying you need roughly a factor of 2 more than, just so you need by counting degrees of freedom. Okay, a little bit less than 2 more because it's 2nd and then there's a tail term. The theorem in phase retrieval says that for such an m, then I can pretty much pick whatever I want for my w's, for my w1 to wm. Just pick random numbers. Almost any choice I make will give me a map that is injective. Okay. And so that is the answer to the question in the phase retrieval setting. This theorem was explored in a series of papers that I write down here, starting from Balan et al. And going through other papers as well. They don't often state this exact one because usually they're interested in like one dimension, and then often they start talking about complex numbers right away. But this is in there. These people do know this, or if you tied them, if you pointed a gun at them and asked them, they would know this answer. And there's also various lower bounds that are somewhat subtle, but they kind of make this tight, or pretty close to tight. So this is pretty much, this is pretty close to this is the truth. Okay. So we talked about graph measurements. We talked about phase retrieval measurements, where basically, yes, you can get injectivity about 2nd minus a little bit. Okay. Good. So where do we come in? So I'll describe our main result, which I will describe, I think best describe as really just a generalization, pretty broad generalization of this phase retrieval result. So let me summarize it. Okay. So what we showed was that ignoring the tail term, that this result, this 2nd result, holds in really incredible generality, and we're going to give some generality here, and then later on I'm going to come back and make it even more general. So let me state the theorem. So let G be a group acting on X. X can be in any vector space R to the big N. In the examples before, X was a matrix in little d times little n, and so you could think of it as a vector in n space where big N is little n times d. But more generally, this could be any vector space. Next, let W in R to the k be a parameter vector. Now, in the previous example, W here was this vector in R to the n. So k was n, but again, we're not going to need that. Okay. Next, let P of xw be a semi-algebraic function over its domain with the following properties. Okay. Here are the properties. Number one, P dot W is group invariant. What do I mean by that? What I mean is, if X is equivalent to Y under my group, then no matter what I pick for my parameters W, Pxw for a fixed W is the same measurement as Pyw. Okay, so think of X and Y are being signals coming from outer space, and W is a knob on my radio. If X and W are congruent, my radio gives me the same answer. Okay, for any way I set the radio. It cannot distinguish equivalent signals. Okay. Now, on the other hand, we want P to be separating, strongly separating. What does that mean? That means if X is not equivalent to Y, these are distinct signals under my group, then for almost all settings of my parameter, my machine P will distinguish X and Y. Okay? So there could be some W that gets them confused and gives me the same output, but that doesn't happen easily because P was chosen to be separating for this group. And when I say almost all, what I really mean is that the exceptional set has a dimension strictly less than the full dimension of my parameter space, R to the k. Okay. So P can be any, Pxw is any, it takes X as a signal, W as a parameter. It never distinguishes equivalent signals, and it almost always distinguishes inequivalent signals. Here's the theorem. Take n, multiply it by 2, and add 1. And let's pick an m which is at least that big. Theorem's going to say that at this point, I'm going to pick my W1 to m. And for almost every choice, I've picked 2 times n plus 1 of these. If I picked a finite set of w's, it's not just finite, it's a small finite set. And now I'm going to look at the functions p dot wi. So for those m finite, that set of w's, I pick those specific parameter settings, which gives me m specific functions p of x. And I apply them to my domain Rn mod G. There's m of these functions making up my map to Rm. And the theorem states that that map will be injective. Okay. So you should see why how this was a generalization, how the phase retrieval fit into this framework with some specific choices for n, k, and a very specific quadratic choice for how p takes the signal and the w, and it does a multiply and takes a d-dimensional norm. And you could go through that example and see that, well, clearly it's group invariant. And you also could convince yourself that that particular measurement system is strongly separating.
Does G need to be defined by polynomials?
Actually, it doesn't. In the original paper, we may have said, in the original archive version, we may have said something about it. But what's really important is just it all comes down, what's all important is P. P is really defined, and in some sense, this is actually you could use this as your definition almost of the orbits and things like that. So G does not have to have any, at this point, any restrictions at all. It really it's all driven by the by how P behaves. Questions? Okay. Here's some details. So P has to be a semi-algebraic function. We'll come back and generalize that a bit more at the end. But in particular, if you don't know what that means, it's pretty broad. It includes any polynomials. In fact, so the phase retrieval, that was just a polynomial function. It includes the rational functions. It also includes other funny things that have if statements, like sorting. And we'll use that later as well. The sorting map from taking a vector of n scalars and giving them in sorted order, that's also a continuous and semi-algebraic map. Okay. In particular, we mentioned this thing, the strongly separating. Almost all the w's, that is a subdimensional set, had to mess up some pair of inputs. If P happens to be, for example, polynomial, then we need a much weaker condition. Okay, all we need is that there exists a W that distinguishes them. Because when you're in polynomial land, if there exists a single W that distinguishes X from Y, then almost all W will distinguish X from Y. The exceptions will have to form an algebraic set, and an algebraic subset can't be full dimensional. So if you thought that this was a strong condition, well, in some cases it can be, but in other cases, like polynomials, this strongly doesn't really add anything at all. And this immediately recovers the phase retrieval results, not counting the tail term. Okay. Now, depending on people and what they like and don't like, this may, this may remind them of Whitney's 2n+1 embedding theorem. So that's a theorem that says a smooth manifold of dimension capital N can very easily be embedded into R to the 2n+1. And notice that there's another Whitney theorem that doesn't have the +1, but in any case, I'm talking about the +1 theorem, and that looks a lot like what we just said. We had a 2n+1, so it does sort of remind you of Whitney's theorem. But it's not technically the same theorem, because if you just Whitney, in fact, starts out if you want to, let's say, implement it, it starts out with an initial very high finite dimensional embedding. and then shows that you can reduce that down to a low number. And so if you were going to implement it, you'd have to start with this high dimensional embedding, and that when we look at some examples with complexity, would be could be exponential cost. Okay, but in what we see here is we're not going to do that at all. We're just going to start with in this particular setup, we're just going to pick 2n plus 1 parameter vectors, and we're going to get the embedding. Let's see. The proof is not that hard. It's really okay. It really is just based on dimension counting, and it is inspired very much by the very first paper over here, the Ballon et al. Paper. So really, we took that proof apart and so saw how far you could push it, basically. There's also an easier result, but we also along the way show it's a bonus result, that if you only want almost everywhere separation, that's generic global rigidity, then you only need n plus 1. If you have n plus 1, then almost all W will work. So in a linear system, n is all you need, and we're saying here in the nonlinear system, you just need 1 more so that you almost always separate. This is, in some sense, you should just, so that's good to know about as well. Any questions? Okay. So now I'm going to give you some other applications of this theory to things. So let's start. So let's go back to our matrix X, which was an R to the D times N. And now I'm interested in taking modulo Sn acting on the right. That means permutations of the n labels of my points. In other words, I have n points in d dimensions, but and I don't get orthogonal transformations in R to the D, right? North is different than up, which is different than east. I know what those mean, but the point labels are meaningless. I really don't know the difference between 0.1 and 0.7. And so I really could permute these at will, and I don't want to think of that as a different matrix. The endpoints are interchangeable, but the d directions are not. So the question is, can I find a small number? Can I come up with a set of measurements that gives me a continuous injective map from this space, R(d_n mod Sn on the right, to an appropriate real space? So here's how we're going to do it. So my W vector is going to be made up of 2 pieces, D numbers and N numbers. Okay, that's going to be 1 W vector. And here's what I'm going to do. I'm going to take my X, and I'm going to hit it on the left with W1 transpose. And that's going to give me just a row vector of length n. Then I'm going to sort that row vector of n numbers. Now I have a different row vector of n numbers. Now I'm going to hit it with a vertical n vector, W2. And that's going to turn this into a single real number. So let me define, that's the sort W1t times x, followed by times the vertical vector WT. And that's going to be my definition of my map PXW to R. Now, I need to check that all the conditions of my theorem apply, namely that PXW is group invariant. Well, that's pretty clear because of the sorting. And check that it is almost always separating, but that can be checked as well. And so our theorem applies. So what does that say? It says we just need to pick at least 2n plus 1 W vectors. So we do this process where W1, W2, that's a random vector, and we have 2n plus 1 of them, and that gives us a continuous injective map to our M. The complexity of evaluating this is roughly quadratic in my numbers. And so it turns out there were other ways that people have talked about dealing with permutations. But at least the immediately previous way required exponentially more work. They essentially required first looking at all the permutations and then later somehow bringing it down to a smaller number of numbers. That's more like somewhat like the Whitney approach in some sense, where you first find a super high dimensional injective map, and then you can drop the dimension down quite a bit after that fact. But that requires that an exponential first step. Questions? Okay, so we've dealt with, starting with x's, we've dealt with O on the left, and then separately we've dealt with Sn on the right. So the natural question is, what about if you want to try to build your group that has both? We want to find an embedding modulo Sn on the right and simultaneously OD on the left. So for starters, you should realize this is already going to be a harder problem because you can reduce graph isomorphism to this kind of thing. And so if you had an efficient way of doing it, you would be doing a lot more than just that. So you probably aren't going to easily figure out how to do this efficiently. And so we can't. So what do we want to do? What can we do? So what we can do is settle for things that are exponential, but only in D, where that's the dimension. And we're interested in low dimension very often, like D is 3 is very typical for these kinds of problems. And it does turn out then that if you have matrices X and you want it to be OD on the left and Sn on the right, you can in fact go to R to the 2nd plus 1. That's going to be our theorem. But the evaluation time is going to take something like this, where your time is exponential in D. Okay. So that's, I don't know if that's good news or bad news. It's the news. You can find a nice embedding. It does go to a low dimensional space, but you're going to need to take a little bit of time to compute where each matrix goes in this embedding. And it's based on some ideas of Curlin, where you find basically a representation that involves multisets of some exponential number of dot products. And so Curlin thinks about this with multisets, but we have this whole trick that can get rid of permutations that we just talked about, which can vectorize multisets. And so if you have a representation, an injective representation based on multisets, then we have a trick that can basically turn that into a vectorization, and that's what we do here. Okay. And now this is going to be the last pretty short topic before I am done. All right. So in everything we talked about, we didn't talk very much about what semi-algebraic set meant, but I assumed that P was a function whose graph is a semi-algebraic set. That's what it means to be a semi-algebraic function. Again, I'm not going to talk about, if you don't know what it is, a semi-algebraic set, but semi-algebraic sets are tame. It's actually a word people use, tame. What does it mean? Well, it means a bunch of things, but here are some of the important ones. First of all, you can stratify it. You can break it up partition it basically into a finite number of smooth manifolds. That's one thing you can say about semi-algebraic sets. In particular, they have a very well-defined notion of dimension. If you take any finite set of semi-algebraic sets and do some finite Boolean operations, what you're going to be left with is still a semi-algebraic set. And then you have this last one. If you take a semi-algebraic set in n dimensions and you project it down to n minus 1 dimensions, the result will still be a semi-algebraic set. And those properties are very tame. In particular, projections mean that you can do quantifier elimination over semi-algebraic sets. So if you have a sentence that has quantifiers in them and semi-algebraicity, you can basically eliminate those things and still end up with a semi-algebraic description, just essentially equalities and inequalities. And this means that these semi-algebraic sets are a very robust and well-behaved family of sets. And you might ask, well, can we relax that? Can we go to a larger class of functions P? There's obvious ones that go by the name analytic or semi-analytic. And the motivation here in machine learning is, suppose P itself is described with a neural network. Now, neural networks, for example, maybe have sigmoids and exponentials, and those are not semi-algebraic. Those, though, are semi-analytic. It turns out it's not so easy to work when you start looking at this. In particular, the semi-analytic class of functions is not preserved under projection, which means that some parts of your arguments can go wrong at some point if there's secretly a projection happening. So we did look at this, and it turned out that there's an interesting relevant topic called O-minimal structures. And it's the study of other families of sets that have a lot of the same tameness of semi-algebraic sets. And so it really started out especially important within logic, but it's also just an interesting study of well-behaved sets. And omitting tons of details, it turns out if you go over our proof from our first paper, we can actually carry over with some slight modifications the whole proof over a much larger family, and the family is called countable unions of globally sub-analytic sets. Okay, I'm not going to say what any of that means, but it does turn out that that family includes analytic and semi-analytic, and so it does include what we think of effectively as neural nets. So if you have a neural net that implements PXW, then our theorems will apply to that as well. And that can be useful, if you're Nadav. Now, as a math person, you say, oh, I can relax, let me keep relaxing. And the question is, how far could you go? Well, the next place maybe was to just assume that P is a smooth function. That's going to be, or piecewise smooth. You could, relax it in that kind of sense. But that seems unlikely or maybe impossible to work in full generality. Smooth functions are going to simply not be tame enough. Even though in Whitney's theorem, he can do his thing in smooth, it doesn't seem like this approach is going to work, is going to carry over. In particular, there are smooth functions. If you look at their zero sets, they don't have you cannot break it up into even a countable number of smooth manifolds. You can get basically Cantor set type behavior. Likewise, you can take smooth manifolds and their intersections might not have a countable stratification, or their projection into a lower dimensional space might not have even a countable stratification. So it seems like if you go to smooth, if you want to think about, oh, I'm going to deal with all possible smooth functions, you're just letting in too many weirdo possible functions that are going to break your arguments and probably break the theorem, in fact. So that's probably too far in terms of relaxing these approaches, but we're not, still staring at that a little bit. And that is what I prepared to talk about today.
Awesome. Let's thank the speaker by smashing one of those reaction buttons. That's how we do it post-COVID, right? I'll stop the recording here and then we'll do questions.